In this video, I'm going to solve the second example problem for our precipitation data. You can follow along on page 8 and 9 of the precipitation module handout available on Camino. So this example asks us to determine the areal average of precipitation over the entire watershed using 3 different methods. And just as a reminder from the reading and the previous videos that you have watched, the areal average is basically trying to figure out how much rain, how much water has fallen in inches over the entire watershed. So you're taking that point gauge data and spreading it over the entire watershed to find the total amount of water that has fallen during a storm. And this is really important for water resource engineers to know how much total water, what volume of water has fallen in a storm in any particular area. So let's go ahead and calculate this average. So I'm going to take the average at each of the stations. So I have 0.55 inches from station A, plus 0.7 inches from station B, plus 2.33 inches from station C, plus 5.4 inches at station D, and lastly 1.89 at station E, and I divide that by 5 to get an average over the whole watershed of 2.21 inches. So this means if I wanted to calculate the total volume of water, I would just take that 2.21 inches and multiply it by the watershed area. So I would probably convert that 2.21 inches to feet and multiply by the acreage of the watershed to get acre feet. Next, we're going to do the same calculation, but using a different method, this one, the Thesian polygon method. So as a summary, here are the steps we're going to follow to determine the areal average using the Thesian polygon method. First, we're going to plot the stations on a map, and that map's going to be drawn to scale. Okay, so we're going to assume for now that this map here is drawn to scale. It's probably not, but we're just going to assume that to make it easier on this video. Then we're going to adjoin the adjacent station locations with straight lines. We're going to take perpendicular bisectors to each line drawn in part 2. And then we're going to have these areas that are drawn. We're going to figure out the area of them. All right, so let's assume that this new map that I've drawn, it's a little bit bigger. It has plotted my stations to scale. I'm going to start by joining the adjacent stations with straight lines. Okay, so I'm going to draw some red lines. And I'll just draw a couple here. All right, so there's a line from A to B. I can try to draw another line from A to C. Okay, so I'm just making all, okay, and now I'm just going to pause it and draw all of the other straight lines. All right, so now I've connected all of the stations. I've done step 2. Now I'm going to do perpendicular bisectors to each of these lines. So I'm going to do that with blue lines. Okay, so there's the perpendicular bisector of the line that goes from station A to station B. So it's perpendicular to that line and it's right in the middle, approximately. That's why you do this to scale. And then you can do the same for the line between B and C. So I'm going to approximate a perpendicular line here through B and C, right through the middle. Okay, so I'm going to do the same again for all of the lines. I'm going to perpendicularly bisect stations B and C, again with a blue line, something like this, right through the middle. And I'm going to go ahead and do that for all of the lines, all the red lines. Okay, so we are done with step 3. So now what we have is we have these areas. So I'll try to do this in a yellow color. So the first one is this area up here that goes with station A. So the way that this Thesian polygon method works is it says that the watershed boundary plus whatever this sort of Thesian polygon is, all of this area, we're going to assume that 0.55 inches fell. Okay, so when we find the area, we're going to do 0.55 times that area. Then I'm going to come over here to station B, and same thing. I'm going to have this watershed boundary, and then these lines here are all going to be associated with that 0.87. Okay? And we do the same thing for station D and station E and station C. And so what we would like to do is actually find the areas associated with each of those. And if you did this properly, which I did not in this case on my app, but you would find that the area associated with A would be 15, let's just say it's square feet. We don't have the units actually. And for B, it's 33 square feet. For C, it's 28.8 square feet. For D, it's 16.4 square feet. And for E, it is 24.3 square feet for a total of 117.5 square feet. So again, what am I saying here? I am saying that this area that I've drawn in yellow is 15 square feet. And this area, which I've indicated in the cyan color, is 33 square feet. And you could do the same for C, which you should get about 28.8 square feet. And for D, you'll get 16.4 square feet. And for E, 24.3 square feet. Okay, so then I'm going to take the 15 square feet, I'm going to multiply that by the precipitation, so that would be 0.55. And I do that all the way down, and you determine so you multiply 15 square feet by 0.55, 33 square feet by 0.87, etc. Divide by that total weight, and you're going to get an aerial average of 2.03 inches. Okay, so we're going to solve this one last time, this time using the iso-Yedel method, which is very similar to the Thesian polygon method, but we're going to do a different weighting technique than what we did in the last one. So the first step in this case is to plot the stations on a map of area drawn to scale, just like we did last time. So here we go. Here's our map drawn to scale-ish. Then we're going to attempt to draw lines of equal precipitation. Okay, so I'm just going to show you a couple here as an example. Again, I'll start with red. So let's say I can estimate a line for 0.5 inches. So this is going to be a lot like surveying, okay? So let's just say this represents 0.5 inches of rain. And then I'm going to do my next one at 1 inch, okay? So I know it's going to be somewhere between A and C, and it's going to be below B and C. So I'm, again, just going to estimate it and say, there is my line of 1 inch of rain, okay? I'm going to keep going on this. I'm going to pause this and add lines for 2, 3, 4, and 5 inches. All right, so there are my approximations for the iso-Yets for 2 inches, 3 inches, 4 inches, and 5 inches of rain. All right, so now I'm going to estimate the precipitation in each grid area. So what do I mean in this case by each grid area? It's quite similar to our previous example. And so I'll start again with A. So this would be the grid area, one grid area that I need to estimate the precipitation in. And then this section, this big section here, would be another area where I would want to estimate the precipitation. Okay, there's lots of ways to do this. One way to do it is just to do the estimate between the two iso-Yets. So this is 0.5 and 1. So let's just say that this is 0.75 inches of rain in here. And then up here, I'm going to say because it's so close to 0.5, I'm just going to call it point, actually it'll be less than that, 0.4 inches of rain. Okay, so you would do the same for each of the different sections. And then you just do the same thing that we did in the previous one. It's a little bit harder to show, so I'm going to get straight to the answer. And so I would have 0.4 inches of rain multiplied by that area. And when you draw this to scale, you can figure out the area just by counting, if you're on a grid, how many grid squares are in that. And then I'm going to do 0.75 times the area shaded in blue, and so on. And then you divide by the total area, just like you did in the previous examples. And if you do this, you are going to get an estimate that the aerial precipitation, meaning if it had rained the same over the entire watershed, that the watershed would get 1.90 inches of rain. So again, we can convert that to feet and then multiply by the watershed area, either in square feet or in acres, to get a volume of water that fell in the watershed during a particular storm.